All right, how's everybody doing? Professor Bryant back, another installment of Workout Wednesday. Today, we're going to be talking titration. Specifically, this is going to be an weak acid, titrated with a strong base. And we're going to look at the stoichiometry, determining pH, and also doing some back calculation to determine concentration. So let's take a quick look at what we're dealing with here. So we have a solution that involves 125 grams of boric acid in 2.5 liters, titrated with 0.25 molar strontium hydroxide. And the first two questions that we're going to try to answer is going to be the pH before we've added any titrant, before we add any base, and the pH when we add a liter of base. Okay, so first thing that we need to do is let's take a look at the chemical reaction that's occurring. So if we go to our reference material, we see that boric acid is H3BO3, and we see that strontium hydroxide has two hydroxides. So the balanced chemical equation is going to involve the creation of water and the creation of the conjugate, right? The conjugate. Remember, H3BO3. If you look at the reference material, we see that it is monoprotic because we only see one Ka, right? We only see one Ka. So here, boric acid, H3BO3, and we see a very low Ka with that monoprotic proton. That means that H2BO3 has to have a negative charge, right? Okay, so to balance this properly, we need a 2 here, and we are creating two waters, right? We're creating two waters. So now we have the stoichiometry. Up until this point, we have not worked with stoichiometry that was not 1-to-1, but you have to take this into consideration. Remember, this comes from General Chemistry 1. Okay, so now that we see the reaction, right? Now that we see the reaction, we need to do some calculations, if you will, on the volumes, right? We need to do some calculations on the mass and the volumes. So up here, I'm going to do this in a little small area. 125 grams of boric acid, so H3BO3. And for every 1 mole, we have 3.03 plus 48 plus boron is 10.81. 61.84, and that is all divided by 2.5 liters. So the concentration of H3BO3 is equal to 125 divided by second answer divided by 2.5, 0.81 roughly, 0.81 molar. Okay. And the first question that we've asked is the pH before any titrant is added, right? And the pH before any titrant is added takes into consideration our friend equilibrium, right? Acid-base equilibrium. So if we are in fact monoprotic and we are dealing with water in solution before we've done any kind of titration, we need to look at the equilibrium with water, and we are going to create hydronium ion and the conjugate base. And this is 1-to-1, right? This is 1-to-1. Now that we know the concentration and we know the Ka value, Ka is equal to 5.9 times 10 to the negative 10, we can then use ice. We're never worried about water. We don't have anything to start. Plus x, x, and we end up with 0.81 minus x, 0.81 minus x. Now, if we take a look at Ka and our concentration, we see that they have a large differential, so we can actually drop x in this, and we can determine the concentration using Ka is equal to x squared over 0.81. And if x is equal to hydronium, which is equal to square root of 0.81 Ka, then hydronium is equal to 2.19 times 10 to the negative 5. And therefore, pH is equal to negative log of hydronium, which is equal to negative log, second answer, 4.66, right? Slightly acidic, right? And that's what we should expect. We should expect it to be slightly acidic because we've been asked to determine pH before any titrant added. So there we are done. Okay, there we are done. So here is before titrant. This is a standard chemical equilibrium acid base. We need to be able to label this HA. This is the base. This is the conjugate acid. This is the conjugate base. And before anything is added, Ka is how we solve this using the ICE table. pH is equal to 4.66. Okay. Now, second question was pH when 1 liter of strontium hydroxide is added. So I'm going to move to the next page. All right. Let's rewrite. I'm going to rewrite the chemical reaction that is of interest. H3BO3 plus SrOH2 gives us H2O2 plus strontium H2BO3 2. All right. So 1 liter of strontium hydroxide is added. So now we do need these moles. So we got the before, we need a limiting reagent, and we need after. But really quickly, we need to do some calculations on this and determine how many moles are actually being added. So we know that the total number of moles that exist in solution of the hydroboric acid or the boric acid, 61.84, is 2.02. So we got 2.02. And the strontium hydroxide number of moles of hydroxide, which is what we're interested in, right, is going to be 0.25 times 1, which is 0.5 moles of hydroxide, again, because that is what we're titrating with. We're not ever worried about water, right? And then to start, we're done with this. Okay, so we have 2 moles, again, of our conjugate, which is leading us to a base, right? This is a conjugate base. So we have to go plus 2x. This is minus x, and this is minus 2x. Okay, hopefully we see what that means right here. The hydroxide here we've already taken in consideration with the 0.5, right? And since this is the limiting reagent, this is minus 0.5. This is minus 0.5. Remember, because X in these cases are the moles of strontium hydroxide, and then this is plus 0.5. And you can do the stoichiometric calculations to determine that, but that is what we are losing, right? We are losing this amount of moles. So here we have 1.52, which is left over. We have no strontium hydroxide, and we have 0.5 moles of the conjugate base, which is what we're interested in. So immediately what we should see is that if we do not have these two values at 0, we are before equivalence point. And since we are before the equivalence point, we need to look at utilizing Henderson-Hasselbalch. So we need to use HH. And to use HH, we need the concentration of H3BO3, which is equal to 1.52 moles all over the total volume. And in this case, the total volume is 2.5 plus 1, so 3.5 liters. And that's equal to 0.43 molar. And then the concentration of H2BO3, which is the conjugate base, which is 0.5 moles all over 3.5 liters. And this is 0.14 molar. Now that we have these two concentrations, we are dealing with a before equivalence point, which means that we are in the buffering region. We can use Henderson-Hasselbalch, and therefore to determine the pH is equal to pKa plus log of A minus concentration over HA, and in this case that's negative log of 5.9 times 10 to the negative 10 plus log of 0.14 over 0.43, and therefore the pH should be still acidic because we are before the equivalence point. So negative log 5.9 e to the negative 10 plus log 0.14 divided by 0.43. Make sure I got that right. Okay, so no, it is not still acidic in this case. I made an improper assumption. We're dealing with 8.74, right? Dealing with 8.74. So because this is such a weak acid, we have an equivalence point. Remember, that's generally going to be in the basic area, and in this case, it is 8.74. So that answers our second question. What happens when 1 liter, again, what happens to pH when 1 liter of our base is added? Okay. All right. Now, let's say that I ask the next question would be at equivalence, what volume of strontium hydroxide is added? This should be a 2 here. Added, and what is pH? Okay, so let's answer the first part of this. What volume of strontium hydroxide is added? We know that the number of moles, 2.02, right? So if we look at just some basic dimensional analysis, 2.02 moles of H3BO3, and for every 2 moles of H3BO3, we only need 1 mole of the strontium hydroxide because it has 2 hydroxides. Now, if we know that the strontium hydroxide is 0.25 moles per 1 liter, now we know volume added. So 2.02 divided by 2 divided by 0.25, 4.04 liters to reach equivalence. All right, so that is the volume, but that involves getting this and understanding that there are 2 moles of hydroxide, so we need 2 of acid, right? We only need half as much. Okay, so now we know the volume. What is the pH? We can then do the stoichiometry, and I'm not going to rewrite this, but you've seen this over and over again, the before, limiting reagent, after. But at equivalence, the same number of moles of acid and base, so therefore you're going to create 2.02 moles of the conjugate. And now you have a basic solution that the volume total is equal to 2.5 plus 4.04. So we're dealing with 6.54 liters now. Okay. Now we're dealing with a reaction that involves H2BO3 and water, and we're dealing with the base reaction in equilibrium, which is going to create hydroxide, right? So now we're dealing with Ka, we know 5.9 times 10 to the negative 10. Kb is equal to Kw over Ka, and therefore Kb is equal to 1 e to the negative 14 divided by 5.9 e to the negative 10. Kb 1.69 times 10 to the negative 5. Okay, so now that we know Kb, we can now look at ice table, because ice table involves concentration. So 2.02 divided by 6.54 gives us the concentration. Looks like 0.31 molar. Remember, we're never worried about water. 0, 0, plus x, 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 minus x, 0.31 minus x. Remember, we can drop x, generally speaking, when the Ka is so much smaller. So we end up with Ka is equal to x squared over 0.31, and x is equal to hydroxide concentration, which is equal to square root of 0.31 times Ka. If hydroxide is then therefore equal to 0.0023 molar, then the POH is equal to negative log of that value, which is 2.64, and therefore the pH is equal to 11.56. So the pH at equivalence is basic. This is what we expect for a weak acid titrated with a strong base, right? 11.56. Okay. Now, the last little bit of this problem that I want to give is a little bit different style of a question, and we can kind of work and back calculate. Let's say that we are at and been given a particular pH, and then back calculate into how much strontium hydroxide has been added. So this is going to be more along the speed of what you should be able to do eventually. Okay, so the before equivalence point was 8.74. So let's talk about at pH is equal to 7.93. What if I ask you how much titrant has been added? Okay, how much titrant has been added to reach 7.93 pH? Right now, this involves understanding your math and being able to back calculate. So, if we think about Henderson-Hasselbalch, which this is in the buffering region, because at the equivalence point we're at 11.56. We just saw for that, right? Equivalence 11.56. So 7.93 is in the buffering region. We are before equivalence point. Therefore, we can use Henderson-Hasselbalch. So to use Henderson-Hasselbalch will allow us to determine total number of hydronium. So if we take a look, right, and understand the equation, we got pH equals pK plus log of A minus over HA. And we know pK, we know now pH. Now we can just solve for A over HA. Okay, and the ratio of A over HA is equal to the pH 7.93 minus negative log of the Ka 5.9 e to the negative 10 which is negative 1.3, and then if we take the inverse of that, we see that we get something that's roughly 0.05. Okay, so we get a ratio or a concentration that's 0.05. All right, now to get this ratio, right, from what we started with, we know that we started with a particular amount of HA that was given to us in the very beginning, right, the concentration. But we also know that this is a function of moles, because at any of this ratio, the number of moles ratio will be the same as the concentration. So we know that from a molar standpoint, right, A number of moles over HA number of moles has to equal 0.05. All right, which means that the majority of these, or the inverse, right, therefore the inverse, HA moles over A minus moles is equal to 20. So we gotta have 20 times more HA than A minus. So if we started with the number of moles of boric acid, which is 2.02 to start, then at what point do we get 20 times that, right? So if we take 0.5 divided by 2, we see that that's 0.25. So we take 0.05 divided by 2, that's 0.025. So we take 0.1 divided by 2, we're at about 0.05, right? So roughly about 0.1 of that needs to be changed, or roughly about 5%, right? So this tells us that we need to change about 5%. That's what this number means. So 5% of this needs to be converted. So what is 5% of this? 0.05. We can multiply that, right? And that is equal to moles of A minus, which is equal to 2.02 times 0.05. That is equal to 0.101. So 0.101 moles needs to be converted. So if that many moles of A need to be converted, then that means that for every 2 moles of our HA, remember we only need 1 mole of the strontium hydroxide, and therefore if we divide that by 2, 0.101 divided by 2, we are left with equaling 0.0505 moles of strontium hydroxide needs to be added. Okay, so now that we know from our percentage, from our ratio, how much of this needs to be added, now we can then convert that into a volume, 0.0505 moles of SrOH2, and we know that for every 1 liter there are 0.25 moles, and therefore we have 0.0505 divided by 0.25, and we're looking at 0.202 liters, which is before the 1 liter that we work with, which makes sense. And so now we are dealing with a volume addition of 0.202 liters, right? So now our volume total is equal to 2.702 liters, roughly, approximately, right? So this is how to use the calculation and back calculate, right? We went, what is the pH of our solution? How much titrant had we added? If we know we're in the buffering region, we have about 5% of our HA converted to A minus. That is what I've shown here, number of moles. And because of that, I can multiply by that value to get how much was converted and convert that using the stoichiometry of the actual original reaction, realizing that this is 2-to-1. Then that gives us this many number of moles, and we can back calculate volume. So that is an expanded type of problem, more along the speed of what you're going to see in the exam. And I went from pH before titrant, pH when 1 liter was added, the pH at equivalence point and how much was added, and then at a given pH, how much was added. So this is a great example of a multi-step problem.